This sound terrified scientists, and nobody knows what made it. In 1997, the loudest unidentified sound in history echoed through the Pacific Ocean. Was it a leviathan from the deep, or something science still can't explain? Deep beneath the Pacific Ocean, the U.S. National Oceanic and Atmospheric Administration, or NOAA, was listening. Using a network of underwater microphones designed to detect Soviet submarines, they picked up something unnatural. The sound lasted just over a minute, but its low-frequency rumble traveled over 3,000 miles. At 238 decibels, it dwarfed the loudest blue whale and matched the volume of a volcanic eruption. But there was no eruption, no earthquake, just this. When the bloop went public in 2002, the internet exploded. Conspiracy theorists called it a sea monster. Gamers claimed it inspired Subnautica's leviathans. In 2012, NOAA declared the bloop was just an icequake. Case closed. Or was it? Because here's the thing. The bloop doesn't sound like ice. It sounds alive, and some scientists think they've been lying to us this whole time. The bloop's eerie resonance has fueled wild speculation, but science demands evidence. To understand why NOAA's Icequake Theory remains controversial and why the mystery endures, we must dissect the physics of sound, glacial behavior, and the frustrating gaps in our data. The bloop was detected by the Sound Surveillance System, SOSUS, a Cold War-era network of hydrophones designed to track Soviet submarines. These underwater microphones work by converting pressure changes into electrical signals, and they're uniquely suited to detect low-frequency sounds, 100 Hz, due to acoustic channeling. Sound waves travel farther in water due to the deep sound channel, a layer where pressure and temperature create a waveguide for low-frequency noise. Ambient noise floor. Below 10 Hz, the ocean is quieter than a library, making faint sounds detectable across thousands of miles. The bloop registered at 238 decibels, louder than a rocket launch, 180 dB, and comparable to the 1883 Krakatoa eruption, 310 dB. However, hydrophones cannot distinguish between biological, geological, or anthropogenic sources. They only tell us something happened, not what. In 2012, NOAA scientists proposed that the bloop was caused by an icequake, a seismic event triggered by glacial fracturing. Antarctica's ice shelves are particularly prone to such events during summer months, November-January, when temperature fluctuations stress the ice. Evidence for icequakes. Frequency match. Icequakes produce ultra-low frequency sounds, or 0.140 Hz, overlapping with the bloop's 1 to 6 Hz range. Seasonal timing. The bloop was detected in May 1997, late in Antarctica's melt season. Similar recordings. NOAA later captured sounds from icebergs calving, e.g., iceberg A5380 in 2009, with comparable acoustic profiles. To balance the information, we need to understand that there are a few problems for the Icequake Theory too. For example, rising frequency. The bloop's sound ascended in pitch over 1 minute, while icequakes typically produce chaotic, irregular waveforms. Epicenter mismatch. The bloop originated in the equatorial Pacific, far from major ice shelves. NOAA argues Antarctic icequakes can propagate globally via sound channels, but this remains unproven. No smoking gun. No icequake has ever been recorded with the bloop's exact acoustic signature. If not ice, what else could generate such a sound? First, methane clathrate eruptions. Methane trapped in icy seabed deposits can explosively release gas bubbles, creating loud, low-frequency sounds. However, these events sound more like sudden pops, like the Juliet sound in 1999, and lack the bloop's tonal sweep. Second, submarine landslides. Collapsing underwater sediment can produce rumbles, but these are typically shorter, seconds, not minutes, and localized. Third, underwater volcanoes. Submarine eruptions generate sustained low-frequency noise, but the bloop's epicenter lacks known volcanic activity. In science, reproducibility is the gold standard. A single observation, no matter how compelling, is often dismissed as an anomaly. The bloop's solitary recording in 1997 epitomizes this problem, leaving researchers grappling with a frustrating truth. Without repeat data, even the most logical theories remain speculative. Here's why. 1. The problem of irreproducibility. The scientific method relies on testing hypotheses through repeated experiments or observations. For example, gravitational waves were theorized for decades before being confirmed in 2015 through multiple detections. Dark matter remains hypothetical, but is indirectly supported by thousands of galactic rotation curves and gravitational lensing observations. The bloop, by contrast, exists in a vacuum. No similar sound has been detected since 1997, despite advances in hydrophone technology and global monitoring. This makes it impossible to confirm patterns. Is the bloop a rare event, e.g. a megathrust icequake or a once-in-a-millennium occurrence? Or to rule out noise? Could it have been a technical glitch? Early SOSUS hydrophones were analog systems prone to interference. 2. Triangulation troubles. To locate a sound source, scientists use triangulation, comparing the time a signal arrives at multiple sensors. NOAA's hydrophone network in 1997 had limited coverage, with only their 6 sensors now operational in the Pacific. This sparse array gave the bloop an estimated origin point spanning 500,000 square miles, an area larger than South Africa. Modern systems, like the Comprehensive Nuclear Test Ban Treaty Organization's CTBTO hydroacoustic network, use dozens of sensors for centimeter-level precision. But in 1997, the technology simply couldn't narrow it down. As a result, biological theories struggle because the bloop's creature could theoretically exist anywhere from the South Pacific to the coast of Chile. Geological theories can't pinpoint underwater features, e.g. methane vents, without a precise epicenter. 3. The new shifting baseline of ocean acoustics. The ocean's soundscape has changed dramatically since 1997. Increased shipping traffic, seismic surveys, and deep-sea mining have raised ambient noise levels by 3 dB per decade, a doubling of noise intensity every 10 years. This means, even if the bloop recurred today, it might be drowned out by human activity. Historical comparisons are flawed, as NOAA's 1997 data reflects a quieter, pre-industrialized ocean. The bloop's haunting sound has inspired one of the most tantalizing questions in modern oceanography. Could a creature larger than any known animal, a true leviathan, exist in the unexplored depths? While NOAA's Icequake Theory offers a tidy explanation, The biological hypothesis persists, fueled by gaps in our knowledge, historical precedents, and the sheer romanticism of the unknown. 1. The size paradox. How big would it need to be? Sound is a product of vibration, and in biological organisms, larger bodies produce lower frequency sounds. Using the wavelength-frequency relationship, scientists estimate the bloop's source would need to be approximately 250 feet or 76 meters long, assuming it's a single organism. To contextualize, blue whales, the largest animals on Earth, max out at 100 feet 30 meters. Megalodon, the extinct giant shark, measured 60 feet 18 meters. Colossal squid, the largest invertebrate, reaches 46 feet 14 meters. This size discrepancy is the biggest strike against the biological theory. No known marine life, extinct or living, approaches 250 feet. Critics argue such a creature would face insurmountable biological challenges. Oxygen demands. Larger bodies require exponentially more oxygen, but the deep ocean is oxygen poor. Prey requirements. A 250-foot predator would need vast amounts of food, yet no ecosystems support such biomass. Stealth paradox. How could a creature this massive evade detection in an era of satellites and sonar? 2. The precedent of the unknown, lessons from the giant squid. Until 2004, the giant squid, Architeuthis dux, was considered a sailor's myth. Its existence was confirmed only when Japanese scientists filmed a live specimen, a reminder that the ocean still harbors secrets. Proponents of the creature theory argue, the deep sea is Earth's final frontier. Less than 5% of the ocean floor has been mapped. Hydrothermal vents, discovered in 1977, host entire ecosystems unknown to science until recently. Cryptic species. The megamouth shark, Megachasma pelagio, wasn't discovered until 1976. The 22-foot giant oarfish, Regalicus glesner, was once dismissed as a sea serpent myth. Deep-sea gigantism. Some abyssal species, like the Japanese spider crab, grow larger than their shallow water relatives. Could this apply to vertebrates or cephalopods? 3. The chorus hypothesis. Many voices, one sound. If a single creature isn't feasible, could the bloop be a collective biological phenomenon, for example? Synchronized whale vocalizations. Male humpback whales sometimes sing in unison during mating seasons. Could a superpod of whales or sperm whales amplify their calls? Squid spawning aggregations. Giant squid may gather in large numbers to breed, potentially creating chaotic noise. Fish schools. The ocean's largest schools, e.g., anchovies, can stretch for miles. Could their combined movements generate low-frequency rumbles? However, even these explanations falter. The bloop's 238 decibel volume exceeds any known biological collective. Its smooth frequency sweep suggests a single coordinated source, not chaos. 4. Why the creature theory endures. The biological hypothesis persists for 3 reasons. 1. Psychological resonance. Humans are pattern-seeking creatures. The bloop's alive quality taps into primal fears of the unknown. 2. Scientific humility. Marine biologist Dr. Edith notes, every time we dive deep, we find something new. To say we've discovered all large creatures is arrogance. 3. Cultural reinforcement. From Godzilla to Subnautica, pop culture primes us to interpret oceanic mysteries as monsters. The bloop's enigmatic sound sits at the crossroads of science and speculation. Most researchers align with NOAA's Icequake explanation, citing the frequency match and seasonal timing of Antarctic glacial activity. The theory is logical, practical, and grounded in observable phenomena. After all, icequakes are common, and the bloop's low-frequency profile fits neatly into this category. Yet, as with many scientific conclusions, practicality doesn't always satisfy curiosity. Critics argue that the icequake theory feels like a bureaucratic shrug, a way to solve a mystery that resists resolution. The bloop's rising pitch and equatorial Pacific origin don't align cleanly with icequake behavior, leaving room for doubt. This doubt is amplified by the ocean's vast, unexplored frontiers. History reminds us that the deep sea has repeatedly defied human assumptions. The giant squid, once dismissed as myth, was filmed alive in 2004. Hydrothermal vent ecosystems, teeming with life in total darkness, rewrote biology textbooks in the 1970s. Could a creature or phenomenon beyond our current understanding exist in the 95% of the ocean we've yet to map? Ultimately, the bloop endures as a cultural icon because it taps into humanity's dual love of mystery and discovery. It's a reminder that science isn't just about answers. It's about questions that propel us forward. While the icequake theory may be the likeliest explanation, the bloop's legacy lies in its power to ignite wonder. As long as the ocean's depths remain uncharted, the door stays open to possibilities, both rational and fantastical. The bloop isn't just a sound, it's a siren call to keep exploring.